So here's what she kind of started off with today, which I think is good. We have the definition of the integral. So we have the integral from a to b of f of x dx, and it's equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I star times delta x. And I just want to remind you guys, right, what this really is this here. Use a different color, right? This, and feel free to ask questions. Why don't I have? Oh, because it's Martin Luther King Day. Chang. It's yeah. We're celebrating the life of Martin Luther King Jr. So f of x of I star times delta x. That's just the area approximation of the ith rectangle, or ith region, I should say. Oh, sorry, I should load the person in. And so I'm going to remind you of the picture we have. So, right, so we're doing this whole deal. You've got some function, f of x. You're breaking, and you're finding the area under f of x from a to b. And you're breaking this up into n sub intervals, which we can't just draw all n, but we can draw some approximation. So, right. So let me point out, because this kind of, the way we label these actually is what's going to help us calculate things. So this is my first subinterval, my first region. This is my second region. This is my third region, all the way till this is, whoops, wow. That's my last region there. There's n of them, right? Because I broke it up into n regions with n subintervals. And the way we label the partition, which is what we call how we've broken this up, is kind of important. So we usually call this first point A, but we also call it x sub 0. And this next one is x sub 1, x sub 2, x sub 3, all the way until the second to last one is x sub n minus 1, and the very last one is x sub n. So it's important to recognize that x sub I star is any x value in the ith interval. So let me draw that one for you. So the first interval has x sub 0 on the left, x sub 1 on the right. The second one has x sub 1 on the left, x sub 2 on the right. The ith one has x sub I minus 1 on the left and x sub I on the right. Or I should say the right endpoint is x sub I, the left endpoint is x sub I minus 1. And so x sub I star can be any point in there. Now here's what we really do. So you could use any point. You can use left endpoint, you can use right endpoint, you can use midpoint, you can use a 3/4 point, you can use anything. But what most people do most of the time is use the right endpoint because it's easy. So while you can define the integral this way, right, where x sub I star is any point between x sub I minus 1 and x sub I, we usually just make this x sub I because it's the easiest way that's still correct to do the calculation. So what we're typically going to do is we're going to actually say that the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times delta x. Okay, so that's one piece we need. We're going to use this definition to calculate some things. The other thing we need is to figure out how we find delta x and how we find x sub I. And that's the part I want to spend just a couple minutes on because it's really easy if we take the time to figure it out. So here's my function I don't really care about. And here's a pen that's starting to eat it. What I really care about is how I'm breaking this up. So here's my A, which is x sub 0. And here's my B, which is x sub n. And I'm breaking this up into, again, these n subintervals. Okay, I want you guys to pay attention. So x sub 0 is equal to A. And each subinterval, the width of each subinterval is delta x, which is the total length. Oh, shoot. Oh, no, I'm good. Sorry, I thought I forgot to come in video for a second. Which is b minus a divided by the number of subintervals, which is n. So delta x is b minus a over n. The reason this is important is because we have to plug in what each of these points is to be able to figure out the formula. So x sub 0 is a. And then x sub 1, well, look, how did I get from x sub 0 to x sub 1? I added a delta x. So x sub 1 is a plus delta x. And then to get to x sub 2, which is right here, I add another delta x. So x sub 2 is a plus 2 delta x's. And as you might guess, x sub 3, we add another delta x on, so that x sub 3 is a plus 3 delta x. So then x sub I, well, x sub whatever is just going to be a plus that many delta x's. So x sub I is a plus I times delta x. And that's what we're going to use to actually calculate things. Is that, so right, so x sub I, that's what's going to go into our function right here in the sum. That x sub I is going to be a plus I times delta x. And we can calculate those things. We can calculate a, and we can calculate delta x as b minus a over n. We're almost ready to do a problem. Just one more thing. The last thing I like to do just to check to make sure that I've actually done this right is to make sure that x sub n turns out to what's supposed to be. So if I was to calculate x sub n, check this out. It's going to be a plus I, sorry, not I. I'm replacing I with n times delta x. But delta x is b minus a over n. So this is a plus n times b minus a over n. The n's cancel, and you get a plus b minus a, and the a's cancel, and you get b, which is what it should be, because x sub n is what b is equal to. So I feel like that's a nice check to see if things are actually correctly set it up. All right, so let's try and actually do a problem. We're going to do an easy one first that we can actually check geometrically. And this is where using those sum formulas is going to be vital. So let's calculate, what have I got here? So we're going to use the limit definition to evaluate the integral from 1 to 3 of 2x plus 1. Okay, so we have to identify a couple things, right? We know, and I just erased it, we know the definition, right? We have over here, all right, that the integral from a to b of f of x dx is equal to the limit, as n goes to infinity, of the sum from I equals 1 to n of f of x sub I times delta x. So really we kind of have to identify three things in my opinion. We have to identify what delta x is, we have to identify what the function is, and then we have to figure out x sub I is. Maybe not in that order. The function should always be really straightforwardly obvious. The function should just be what is in the integrand. So right, the thing you're integrating is called the integrand. So there's your function f of x. Okay, so we need delta x, which is just b minus a over n, which is 3 minus 1 over n, which is 2 over n. And then we need x sub I. You don't have to draw a picture, but I'm going to draw a picture here. So, yeah, sorry, I'm starting to, my pen, I need to refill some of my pens here. So, right, 2x plus 1 is just a straight line. It's kind of like this. And I'm going from 1 to 3. I'm trying to find this area here. And the idea here, oh, what is it? I was trying to say something. Oh, yeah, we could just, yeah. We're going to calculate that in a minute using just like the rules for areas of things. But what I was trying to say is, right, is we're breaking this up into n subintervals. And what I'm trying to say is you don't have to draw this picture every time. I like drawing to kind of point out what's happening, but really you can just say, if you can remember the formula for x sub I, you're good to go. X sub I is a plus I times delta x, which in this case is, well, our a value is 1, I is just I, and delta x we just found was 2 over n. So you could write this as 1 plus I times 2 over n, or you could simplify it slightly, write it as 1 plus 2I over n. And so let's see if that makes sense. Here's x sub 0. X sub 0, if I plugged in 0 for I would get 1 plus 0, which is 1. Here's x sub 1, which should be 1 delta x further to the right. If I plug in 1 for I, right, here's my x sub I get 1 plus 2 times 1 over n. I get 1 plus 2 over n, which is exactly 1 plus 2 over n, 1, which is a delta x away. So this is looking correct. All right, and then we need to figure out what f of x sub I is. So we know that f of x is 2x plus 1. So f of x sub I is going to be 2 times x sub I plus 1. All right, so now we're ready to calculate this mess here. And I think I'm going to want to use the other side of the board, because I will say you want to give yourself room on these problems, because it's just a lot of writing stuff again and again and again. So these problems do take up a lot of space when you're trying to figure them out. So yeah, don't worry, we'll come back to it. So I'm trying to write the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. And that's going to equal the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I. That's this thing here, 2 times 1 plus 2i over n plus 1. I might want to simplify that, but we'll see. Times delta x, which is 2 over n. Questions about this before we start making a mess? All right. The whole entire goal here is to ignore the limit. I mean, we're going to write it each step, but we're going to ignore it until the very end. And to write this sum as a sum that has, we want to write it so it looks something like a number times the sum of I plus a number times the sum of just 1. We want to be able to get the sum of I so we can use that formula. We know that the sum of I is n times n plus 1 over 2. So that's why we talked about those formulas before, because we have to use them here. So let's simplify this. Let's see. This is going to be limit as n goes to infinity of the sum from I equals 1 to n. So let's see. This is going to be, I'm going to do a little bit of work here. So distributing this is 2 plus 2 times 2i over n is 4i over n plus 1. So 2 plus 1 gives me 3. So I've got 3 plus 4i over n times 2 over n. And then I can distribute the 2 over n. So you get the limit as n goes to infinity of the sum from I equals 1 to n. If I distribute the 2 over n, I get 2 over n times 3 is 6 over n, and 2 over n times 4i over n is 8i over n squared. And I'll give you a tip. Every time you're doing this limit definition sum thing, if you're trying to actually calculate the limit here, what you always need to happen when you get to this stage where you have just fractions is the power of n in the denominator should always be exactly 1 greater than the power of I in the numerator. That's what we always need to happen for this to work out. Here we have n squared, here we have I to the first, we're good. Here we have n to the first, up here we have I to the 0th, no i's. So we're good, so we're safe. I know it's gonna work out. So we're gonna break this apart. I'm gonna write this as the limit as n goes to infinity of the sum from I equals 1 to n of 6 over n plus the sum from I equals 1 to n of 8i over n squared. And then the last step, the last step before we use the formulas, you can take the 6 over n out in front if you want, or you can leave it. It's just a constant. So I want to be careful here, right? N, as far as this sum is concerned, is just a number. It could be 5, it could be 1,000, it could be 1,000,000,000, but it's just a number. It's not changing until we take the limit, and we're not taking the limit yet. So what I'm really trying to say is, as far as the sum is concerned, the only thing that's a variable is the index I. Since there aren't any i's here, we can take this whole constant out. So you could write this as the limit as n goes to infinity of 6 over n times the sum from I equals 1 to n of 1. So people like to do it this way and then say that the sum of this is n, right? Because it's 1 plus 1 plus 1 plus 1 n times, and then 6 over n times n is just 6. Or some people just like to leave it like this and just say it's 6 over n times n, which is 6. That one, this first one is either way is kind of fine. The second one, I really do recommend pulling out everything that's not the I. So I would write this as plus the sum, plus 8 over n squared times the sum from I equals 1 to n of I. And now, see, these problems are really always like such a process, like so much work to get there. So let's see what we've got. So I've got the limit as n goes to infinity of 6 over n times n, right? The sum from I equals 1 to n of 1 is just n, plus 8 over n squared times the sum from I equals 1 to n of I is n times n plus 1 over 2. All right. I personally like to do as little work as possible at this stage, but here's the work you could do. So if we multiply these out, well, this first one is just 6. So the limit as n goes to infinity of 6. Plus, if we multiply the second one out, in the denominator, we get 2n squared. In the numerator, so n times n plus 1 is n squared plus n. Multiply that by 8, you get 8n squared plus 8n. Can anyone write in the chat what the limit of just this part is as n goes to infinity?
It's 4.
Yeah, it's totally 4. And the way we know it's 4 is because, right, you got a rational function where the highest degrees in the top and the bottom are the same, or the degree is the same, is what I should be saying. And so, yeah, you get the quotient of the leading coefficients, which is 8 over 2, which is 4. So our answer is 6 plus 4, which is 10. Okay, so now let me point out that, yeah, an equally valid way to have found the area here would have been to find the area using a rectangle and a triangle. You could also use a trapezoid formula. I never remember the trapezoid formula. I would break this up as a rectangle with a base of 2 and a height of, let's see, when I plug in 1 to my function, which is 2x plus 1. This height is 3. When I plug in 3 over here, this height is 3 times 2 plus 1 is 7. So this rectangle has a base of 2 and a height of 3. This triangle has a base of 2 and a height of, let's see, this is 3, so this is supposed to be 4. 7 minus 3 is 4. So it's got an area of 1/2 of base times height, which ends up being exactly 6 plus 4, which is 10. So the reason I say this is just to point out that the formula actually really literally does work, right? We can find the area using geometric methods, but we can also find the area depending on the function, because some functions are really a lot more challenging to do this process for, but we can find the area using this whole limit definition of the integral. We'll do another example, maybe two, but I want to ask you guys, are there questions about what we have done here? All right, let's do another one. So here's what I'll say about this. Most of the time, the only types of functions we can really do this for with relative ease are polynomials, right? So you will probably only ever actually be asked to do this if the function is like linear or quadratic or maybe cubic. But other kinds of functions really don't lend themselves to being evaluated like this very easily. So I would have to imagine you're not going to get asked other types of things other than just nice positive integer powers of x. So let's look at, sorry, I lost my stuff here. Yeah, that's definitely true. Like the problems that are in the book in section 5.2, the only ones where they ask you to do this are problems like 19 through 23, and those are all polynomial functions. So let's do another one. We'll try and do this one a little bit faster. And I think it might help. Yeah, so I'll try and show you a way to make it go maybe a little bit less writing. So let's try and do this. That one seems less exciting. Fine, it'll be fine. Fine. Let's do the integral from, let's try and calculate the integral from 0 to 2 of 3x squared plus 4 dx. So again, this is going to give us the area under the curve 3x squared plus 4 from 0 to 2. So it's going to look something like this. 3x squared plus 4, it looks the parabola, it looks like that. And if we're going from 0 to 2, right, we're getting this area here. Now I'll point out that unlike before, we can't just calculate the area using geometric formulas, where we actually have to calculate the area using the integral, because there aren't other good, well, there technically is a way of doing it, but like there really aren't usually other good ways. So we're going to do the same thing. We're going to find the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. And so what I would maybe recommend is actually calculating f of x sub I times delta x and simplifying it as much as possible before throwing it into this. So let's over here say, well, okay, my function, let's do the function last. So delta x is b minus a over n, which is 2 over n. Yeah, x sub I. So x sub I is a plus I times delta x, which in this case is 0 plus I times 2 over n, or just 2I over n. And then f of x sub I. So I know that f of x is 3x squared plus 4. And that's my f of x. So f of x sub I is just going to be this same function, except wherever I see x, I'm going to put x sub I instead. And x sub I is 2I over n. So my f of x sub I is going to be 3 times, not x squared plus 4, but x sub I, which is 2I over n squared plus 4. And I think it's going to be in our best interest to find this over here and simplify it. So f of x sub I times delta x is, well, let's see, f of x sub I, I'm going to multiply this out. So I'm going to get 3 times 2i over n squared is 4i squared over n squared plus 4. And it's all of that times my delta x, which is 2 over n. So let's simplify this a little bit. The 3 times this is going to give me 12i squared over n squared plus 4, all times 2 over n. And then finally distribute the 2 over n and get 24i squared over n cubed plus 8 over n. So I think doing this simplification without having the limit and the sum in each step is a lot less writing, right? Look over here where I was doing all of my algebra while carrying the limit and the summation with each step. I think that's probably less efficient to do it that way. So I would encourage everyone to, if you're calculating this, do the work for this part on its own so it's simpler to deal with. All right, so then we've got the following. With the limit as n goes to infinity of the sum from I equals 1 to n of this thing here. 24i squared over n cubed plus 8 over n. And again, I notice that I'm in the right spot, meaning my powers of I on top are exactly 1 less than my powers of n on the bottom. I to the second, n to the third, I to the 0th, n to the first. So good, I'm safe. I would encourage you to do the breaking up and the factoring out of constants in one step. Meaning I'm going to break this up into 2 sums. It's going to be the sum I equals 1 to n, sum from I to n. And here I'd pull, so for the second one, which would be 8 over n, I'd pull out the entire 8 over n and be left with 1. For this one here, which is 24i squared over n cubed, I'm going to leave the I squared in, but I'm going to pull out in front the 24 over n cubed. Then we get to use the formulas. So this is equal to the limit as n goes to infinity of 24 over n cubed times the formula for the sum of I squared, which is n times n plus 1 times 2n plus 1 all over 6 plus 8 over n times the sum of 1, which is just n. And these obviously cancel right away. So here's the thing. I really don't like to have to multiply out n times n plus 1 times 2n plus 1. And I really don't have to. Here's what we can see. We can see that in this rational expression, if you were to multiply out the bottom, you would get a 6n cubed. If you were to multiply out the top, well, I have an n times an n plus 1 times a 2n plus 1. My highest power of n would also be n cubed. If I have 24 times n plus 1 times 2n plus 1, what's the coefficient of n cubed going to be when I multiply out that top part? You can type it. Yeah, type it. Sorry, I'm running out of room here, I know.
48.
It would be 48 because it's a 24, but there's also a 2. So here's what I'm going to have on top. I'm going to have 48 n cubed plus I don't care. Those smaller powers of n don't matter. If she wants you to multiply that, you definitely should. But what I'm saying is you don't really need to multiply that part out to know what's going to happen here. And then this part's still plus 8. So the limit of this is going to be 48 over 6. So you get 48 over 6 plus 8, which is 8 plus 8, which is 16. And that's what we get. It's certainly fine to multiply this all out, and it's not like it's that much work. It just feels unnecessary to me. So that's what I will say about that. So questions here.
I have a question. How did you get 48?
Sorry, go ahead. Say it again.
How did you get 48?
Sure. So let me show you. So let me show you the work that I skipped. So if we multiply out the top and the bottom for real, so on the bottom I get 6n cubed. I also got this plus 8 over here. On the top, if you multiply this out, so I've got n times n plus 1 times 2n plus 1. So n times 24. So I've got 24n, and then n plus 1 times 2n plus 1 is, let's see, it's 2n squared plus, let's see, 2n plus n is 3n, and then 1 times 1 is 1. So I've almost finished multiplying it out, and if I do one more step, 24n times 2n squared is 48n cubed, and then 24n times 3n is 72n squared, and then 24n times 1 is 24n, all over 6n cubed. So we could do all this work and then see that the limit is still going to be the quotient of the leading coefficient, which is 48 over 6. So what I'm looking for to not do the work and still know what the leading term is to look at all the power, all the things with n. So what I really did was I said I have a 24 times an n times an n times a 2n there. So that's how I got 48n cubed.
Thank you.
You're very welcome. Yeah, of course. Yeah. So that's kind of most of what there is there. The other thing people sometimes ask you to do with this kind of stuff is to either take an integral and write it as the limit definition without actually calculating it, or to go backwards, to start with the limit definition and tell them what the integral would be. So let's do a couple of those. I think those are good practice. And I know someone said problem 16 and 18 were ones you did. The second thing I said, taking, all right, 16 and 18. Yeah, taking the limit expression and turning it into an integral is what those are all about. And they give you the limit to integration. Okay, cool. So let's take a look at this one. Let's do the integral from 2 to 6 of x over 1 plus x to the 5th. And our job here is to write this as the limit definition of the integral. We're not going to evaluate it because it's really, really challenging. Like, I have no idea how you would actually do it. But we don't need to. In fact, I don't even know if this, No, this function can be integrated. Later on, we'll learn how to integrate something like this. It'll be fun. Yeah, it'll be fun. I mean, fun, right? Okay. So we know it's going to be, we know we're looking for the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times delta x. That's an interesting question I hadn't thought about. Yeah, huh. Yeah, I'll give two equally good answers here just to kind of show you guys something. So our function is definitely what's inside the integral, x over 1 plus x to the 5th. And then we need delta x and we need x of I. So delta x is 6 minus 2 over n, which is 4 over n. And x of I, again, remember x of I is a plus I times delta x. So that's a plus I times delta x, which in this case is 2 plus I times 4 over n. Okay, that's fine. And so then f of x of I would be this function with that subbed in for each x. So it would be 2 plus 4i over n over 1 plus that same thing, 2 plus 4i over n to the 5th. I would not bother with simplifying this. So then I'm going to write this as the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I, which is this mess here, 2 plus 4i over n over 1 plus 2 plus 4i over n to the 5th times delta x, which is 4 over n. And I would leave it like that. I wouldn't touch it. It looks terrible as is. But that's what they're kind of, when the function is terrible, that's what they're kind of asking you, just to write the limit definition. And this would be, I have no idea how one actually would evaluate this using the limit definition. I don't know if it's actually really possible to do using the limit definition. That's okay. We're not being asked to do that. The other thing people like to do is go the other direction, meaning, I said I was going to give you a, so you could do it this way. This is the way you should do it. But I will point out, no one actually said you had to use right endpoints. So if you wanted to get super fancy, you could use left endpoints to say, well, instead of using x sub I being a plus I times delta x, I'm going to use x sub I minus 1, right? X sub I is the right endpoint. X sub I is the left endpoint, which is a plus I minus 1 times delta x, which is 2 plus I minus 1 times 4 over n. And maybe you can already see why this is a worse choice, because writing this is going to take up even more space than writing 2 plus 4i over n. So an equivalent answer would be to say it's the limit as n goes to infinity of the sum from I equals 1 to n of, okay, it's going to be terrible. I'm going to write this as 4 times I minus 1 over n. So it's going to be 2 plus 4 times I minus 1 over n over 1 plus 2 plus 4 times I minus 1 over n to the 5th, all times 4 over n. So hopefully this helps convince you why we usually use right endpoints, because they just take up a little less room to write. They look a little nicer. But this would be the way of writing the limit definition of the area of this particular expression using left endpoints instead of right endpoints. And as I think she was about to say as I was leaving class today, was that it doesn't matter if you use left or right, because as you're letting the width of all of your rectangles get super duper infinitesimally narrow, the left endpoints and the right endpoints and the midpoints all essentially get super close to each other. So they're really giving you the same height. So it doesn't matter. So that's why you can pick any x sub I star in between the two, the left and the right endpoint. You can also use midpoints, which would be even worse. Not going to do that. Okay. The other thing people like to do, or like to ask you to do, is to take something like the following. Let's say I want to find, so I want to write the following sum as a definite interval. So here's an example. Where'd you go? The limit as n goes to infinity of the sum from I equals 1 to n of the sine of, what do we got here? 2x sub I star plus x sub I star squared times delta x. Now personally, yeah, wow. So I feel like they've made this a little easy. That's all right. It's okay if it's easy. I've definitely seen harder versions of questions like this, but we don't need to make things artificially hard if we don't need to. I love to say in the 21 series, when they ask these questions, they do make it a little less easy to see what everything is. But here we're basically just saying, okay, well, sorry, I have to give you the, and they also give us the interval. On the interval from, let's say, 2 to 9. So it's really kind of straightforward. The limit of the sum part, that kind of transforms into the integral symbol. The limits of integration are given from 2 to 9. And then the delta x becomes your dx. And x of I becomes just x. So it's sine of 2x plus x squared. And that's really kind of it as far as this textbook is concerned. You take, right, I mean, you just transform things. Right? The limit of the sum becomes the integral. The function stays the same, except the x of I stars or x of i's, whatever they are, become just x's. And the delta x becomes a dx. That's really kind of all there is to it. It feels like it would be silly to do another one. Here's okay. Yeah, here's a better question. Good. Okay, there are a couple harder ones. Yeah, problems 47 and 48 in section 5.2 are a little more challenging. Let's look at 47. I was like, they can't all be this easy. So let's look at this one. So again, we want to write this as a definite interval. Expressed as a definite interval. And I don't know if you talked about this, but when we say the words definite integral, I mean an integral that has limits of integration. Later on, we'll start talking about indefinite integrals, which is another way of writing an antiderivative. So, but the definite integral is just always trying to express an area. So we have the limit as n goes to infinity of the sum I equals 1 to n of I to the 4th over n to the 5th. Now, interestingly, I will point out we could calculate this if we knew the formula for the sum of I to the 4th. It definitely fits the, it looks the way it's supposed to look, where the power of I is 1 less than the power of n. So you could calculate this if you really wanted to. We're not going to. What we're going to do is we're going to write it as an integral. So here, unlike before, we have to figure out what is delta x and what is x of I. And then what is the function? And this is kind of where things are a little bit challenging. So you kind of want to think about taking the path of least resistance here. Delta x is usually something divided by n, like 2 over n, or 3 over n, or 1 over n. I don't see any numbers other than 1, right? Like I don't see a 2, a 3, a 4, or 5. So I would think, oh, my delta x is probably 1 over n. So I might rewrite this as the sum, the limit of the sum from I equals 1 to n of I to the 4th over n to the 4th times 1 over n. Because then this can probably play the role of delta x. Okay. So if delta x is 1 over n, that's your b minus a over n. So here's kind of something that's interesting. You can usually kind of pick whatever you want for b and for a, as long as they subtract to 1. It does make it, it'll come out nicer if you pick the right thing, but really you can pick anything. I would pick, unless there was a reason not to, I would pick my b minus a to be 1 minus 0. And the reason for that is because then x sub I is going to be nice. X sub I, if you recall, is a plus I times delta x. Well, a is 0. and I times delta x is I times 1 over n. So look, your x of I is I times 1 over n, which is I over n. And that's good because we have I to the fourth over n to the fourth, or if you prefer, I over n to the fourth power. Well, look, now it's becoming pretty clear what's what. There's my x sub I to the fourth. There's my 1 over n. So this, if I wanted to rewrite this before I write it as an integral, I could say, well, this is looking a heck of a lot like, so right here, the sum from I equals 1 to n of, sorry, the limit, I keep reading the limit, of x sub I to the fourth times delta x. And now it's much easier to transform that into the integral. Oh, that's the integral of x to the fourth times dx from 0 to 1. Because, right, a was 0 and b was 1. Oh, wow, it's 3 o'clock.